Over the past several years, I've built several applications related to Taekwondo. But one of the most interesting projects I've worked on is an AI assistant design specifically to answer Taekwondo questions. The basic idea sounds simple. Allow someone to ask a question about a form, tournament rule, judging requirement, or technique, and receive an answer. But building an AI application that produces reliable answers is much more complicated than simply connecting text to an AI model. In this video, I'm going to walk through how this project evolved from a simple Flutter prototype into a hybrid AI architecture that uses trusted PDF documents, semantic search, Supabase, and an embedded Gemma model running directly on the device. I'll also explain why cloud building forced me to rethink the original architecture, how I built a retrieval augmented generation system, and why I eventually needed a dedicated test harness to determine whether the answers were actually correct. The original goal was to create an AI assistant focused specifically on Taekwondo. There are a lot of Taekwondo manuals, tournament documents, judging guides, and reference materials. The problem is that the information is spread across many different documents. Even when someone has access to all of those documents, finding a specific answer can be difficult. You may need to open several PDFs, search for slightly different terms, and determine which document contains the most current or relevant information. I wanted to make that process easier. Instead of manually searching through multiple PDFs, the user could ask a question in plain English and receive an answer based on trusted Taekwondo reference material. Because I'm a Flutter developer, I also wanted to deliver the assistant through a cross-platform Flutter application. The vision was a specialized AI assistant that could provide useful, domain-specific answers without requiring the user to understand where the information was stored. I began with a relatively simple Flutter AI application. The first version had just a text field and a mic icon for asking a question. The user entered a question, the application sent that question to a general-purpose language model, and the model returned a response. This was enough to allow me to enter something and then test the app to see if I got a response. Originally, I would just pass the question on to Google's Gemini in the cloud. This worked well in testing. AI also played a role in building the application itself. I used AI tools to propose screen layouts, navigation flows, interface ideas, and different ways to present the model's responses. For example, AI could suggest how the text field should be shown, where source references should appear. That accelerated the early design process, but I did not simply accept everything the AI produced. AI was acting as a development assistant, not as an autonomous engineer. I still had to evaluate the suggestions, decide which ideas were appropriate, implement the application architecture, and verify that the generated code behaved correctly. AI was particularly useful for generating alternatives and helping me iterate quickly. However, decisions involving user experience, Flutter architecture, performance, security, and domain accuracy still required manual engineering and review. That distinction becomes even more important when the application itself uses AI. AI may help you to build the product, but that does not mean it can independently determine whether the product is correct. The first working architecture relied entirely on cloud-based AI. The Flutter application set each question to a cloud-hosted language model. The cloud model processed the question and then generated the answer. This approach had several advantages. It was easy to integrate. The cloud models had strong general language capabilities. I didn't have to package a large AI model with the application. And I didn't need to worry about whether the user's phone had enough memory or processing power to run the model. From a technical standpoint, the first version worked. But once I started thinking about releasing the application to more people, I encountered a significant problem. The app worked, but could I afford to let people use it? Cloud-based AI normally uses usage-based pricing. Every time a user asks a question, the application incurs a cost. That cost might include language model inference, embedding generation, database operations, server usage, and network traffic. For a small prototype with only a few users, those costs may be almost unnoticeable, but the cost increases as more people use the application. That creates a difficult business problem for an inexpensive or free app. The more successful the application becomes, the more expensive it becomes to operate. It can also be difficult to predict the cost because not every question uses the same number of tokens. A short question with a short answer may cost very little, while a longer conversation containing a large amount of context may cost considerably more. Suddenly, billing limits, provider quotas, rate limits, and cost controls become part of the application architecture. You have to consider questions such as, what happens if someone sends hundreds of questions? Should each user have a daily usage limit? Do I need to require an account? Do I need a subscription? What happens if a bug repeatedly calls the model? And what happens if the cloud provider changes its pricing? I didn't want the long-term viability of the application to depend entirely on paying a cloud provider every time someone asked a question. I released the app to the public, and while there were not many users, I got an email stating that I had reached a limit on my AI usage. That meant my app was dead. No one could use it. While I tried to fight to get my limit increased, no one could use the app. This was not acceptable. I had to find another way. I began reevaluating which parts of the AI workflow truly needed to run in the cloud. There were several competing concerns. I wanted good model quality, but I also wanted acceptable performance. I wanted to protect user privacy. I wanted the possibility of offline or limited connectivity use. I wanted to keep the application download reasonably small. I wanted to reduce the size of any model that had to be downloaded. And most importantly, I wanted to reduce the ongoing cost of operating the application. There was no perfect solution. Running everything in the cloud offered powerful models and simpler device requirements, but it created recurring cost and required every question to leave the device. Running everything locally reduced cloud dependency, but it introduced application size, memory, performance, and model quality constraints. The architecture needed to balance those trade-offs. I eventually decided to move the final response generation onto the user's device. The next version of the application embedded a Gemma language model directly in the app. Instead of sending every question to a remote language model, the application can run the model locally and generate the response on the device. That fundamentally changed the cost model. Once the model was downloaded, generating another answer did not create another cloud inference charge. It also improved privacy because the user's complete question and generated response did not need to be sent to a remote AI provider. On-device inference also made offline or limited connectivity scenarios possible. However, moving the model onto the device introduced a new set of engineering problems. The application or model download became larger. The device needed enough memory and processing power to run the model. Responses could be slower, particularly on older or less powerful hardware. Different Android devices could produce dramatically different performance. And smaller local models generally do not have the same capabilities as the larger cloud models. A smaller model can answer questions well when it receives focused, high-quality information. But if the model receives poor content or no relevant content at all, the quality of the answer can decline quickly. That meant I could not simply put a smaller model onto the phone and expect it to know every detail about Taekwondo. I needed a way to provide the model with the correct information for each question. The next step was building a trusted knowledge base from Taekwondo reference documents. I collected the official or trusted PDFs that I wanted the application to use. Then I extracted the text from those documents. PDF extraction sounds straightforward, but the resulting text is often messy. Headers and footers may appear repeatedly on every page. Page numbers may be inserted into sentences. Columns may be read in the wrong order. Tables may lose their structure. Words may be split incorrectly. And the same text may appear multiple times. Before the documents could be used effectively, the extracted content had to be cleaned. I removed repeated headers, footers, duplicated content, and obvious formatting artifacts. Then I divided the text into smaller, meaningful sections called chunks. Each chunk needed to contain enough information to be useful without becoming so large that it overwhelmed the model. I also preserved metadata for every chunk. That metadata could include the document name, page number, section, rank form, subject, category, or other identifying information. The metadata was important for two reasons. First, it helped the retrieval system narrow its search. Second, it made it possible to show the user where an answer came from. All of this was done using AI and Python scripts. Once the documents were divided into chunks, I generated an embedding for each chunk. An embedding is a numerical representation of the meaning of a piece of text. One way to imagine an embedding is as a set of coordinates in a very large multidimensional space. Text with similar meaning tends to have coordinates that are closer together, even when the text does not use exactly the same words. This is important because traditional keywords search depends heavily on exact wording. A user may ask about the meaning of a technique using different terminology than the manual uses. Semantic search can still identify that the question and the relevant document section are conceptually related. I stored the text chunks, their metadata, and their embeddings in Supabase. Supabase supports vector search through PostSQL and pgvector. When the user asks a question, the system can search for the document chunks whose embeddings are most similar to the embedding of the question. This allows the application to retrieve only the most relevant pieces of all the manuals. It does not need to send entire documents to the model for every question. These embeddings are done one time on a Mac and uploaded to the Supabase database. If done correctly, they should only need to be uploaded once. However, the AI and I determined that more information was needed, so multiple processing was done. This produced the hybrid architecture used by the application. Here's the complete workflow. First, the user asks a question in the Flutter application. Supabase performs a vector search and finds the PDF chunks that are most semantically related to the question. The application receives only the best matching source material. That retrieved context is then passed to the embedded Gemma model. Gemma uses that context to generate the final answer directly on the device. The Flutter application displays the answer along with its supporting document references. A simple way to describe the architecture is this. Supabase retrieves the knowledge, Gemma interprets that knowledge, and Flutter presents the experience. This architecture does not completely eliminate network usage because retrieval may still involve Supabase, but it substantially reduces the expensive part of the process, generating every answer with a remotely hosted language model. The formal term for this technique is retrieval augmented generation, usually called RAG. The language model does not need to memorize every piece of Taekwondo information. Instead, the system retrieves relevant information when the user asks a question. The model receives a small, focused collection of source material and uses it to generate the answer. This approach offers several advantages. It improves the likelihood that the response is grounded in trusted documents. It allows the application to use a smaller model because the model does not need to know everything on its own. It reduces the amount of context that must be passed into the model. And the knowledge base can be updated independently of the model. For example, if tournament rules change, I can update and re-index the relevant documents without retraining the Gemma model. The model remains the same while the retrieved knowledge changes. The first version of the retrieval system did not automatically produce perfect answers. Several settings had to be tuned. One of the most important was chunk size. If a chunk was too small, it might contain only part of the information needed to answer the question. If it was too large, it might contain irrelevant details and consume too much of the model's available context. I experimented with chunk size and overlap so that related information would not be accidentally separated. I also adjusted how many matching chunks were returned for each question. Retrieving too few chunks could omit important information. Retrieving too many could introduce unrelated material and confuse the model. Similarity thresholds were also important. If the search results were not sufficiently similar to the question, it was often better to say that the documents did not contain an answer than to provide weak context to the model. I also refined the system prompt. The model was instructed to answer only using the supplied context. It was told not to invent an answer when the source material was insufficient. It was also instructed to identify uncertainty and point out conflicting source material. Where possible, the response included the document name and page number. These controls reduced hallucinations, but they did not eliminate the need for testing. AI output is non-deterministic. The same question can produce slightly different wording, or sometimes a meaningful different answer on separate runs. A response can also sound confident and professional while still being factually incorrect. That makes casual manual testing dangerous. You can read an answer, think it sounds reasonable, and assume the system is working. But it sounds right is not a test strategy. The architecture also had many interacting components. I could change the model, system prompt, embedding model, chunk size, similarity threshold, retrieval count, or source documents. Improving one part of the system could accidentally make another part worse. Manual testing did not scale across all of these combinations. I needed a repeatable way to determine whether a change actually improved the application. That led to the creation of a dedicated test harness. The test harness contained Taekwondo questions retrieved from the PDF documents themselves. I used AI to create that list of questions by going through the PDFs to get the question and the answer. For each question, I could define the facts that a correct answer should contain. I could also specify which source document or section should be retrieved. The test set included several categories of questions. Some were simple factual questions with a clear answer in one document section. Others required information from multiple chunks. The correct behavior was not to invent a plausible rule. The correct behavior was to state that the available documents did not contain enough information. After changing the prompt, model, chunking strategy, or retrieval settings, I could run the same questions again. This made it possible to compare results instead of relying on memory or subjective impressions. This project produced several important lessons. The first is that a successful prototype is not necessarily a sustainable product. The original cloud-based version worked technically, but its operating costs would have increased with every user and every question. Cloud AI costs need to be considered early, not after the application becomes popular. The second lesson is that on-device AI does not eliminate complexity. It trades ongoing inference cost for engineering complexity. You have to manage model size, memory, initialization, device compatibility, and response speed. The third lesson is that smaller models depend heavily on high-quality context. A focused model with the correct source material can perform surprisingly well. But even a powerful model will produce poor results if the retrieval system gives it the wrong information. Fourth lesson is that PDF preparation matters. Document cleaning, chunk boundaries, metadata, and source organization directly affect the quality of the final answers. The fifth lesson is that retrieval and generation should be tested independently. You need to know whether the system found the wrong information or whether the model misinterpreted the correct information. And finally, domain expertise remains essential. AI helped me design and build the application. It helped generate code, propose interfaces, refine prompts, and explore architecture options. But it could not independently determine whether every Taekwondo answer was correct. That still required knowledge of the domain. The final system combines several technologies, each with a specific responsibility. Flutter provides a cross-platform application and user experience. Supabase stores the processed document chunks, embeddings, and metadata. Vector search identifies the source material most relevant to the user's question. The embedded Gemma model interprets that material and generates the answer locally. The test harness measures retrieval quality, answer accuracy, performance, and regressions. The result is an architecture that reduces recurring AI inference costs while still providing answers based on domain-specific source material. It also improves privacy and creates the possibility of operating with limited connectivity. The system is not completely offline yet because document retrieval may still require a network connection, but it is a significant move away from an architecture in which every question must be processed entirely by a paid cloud AI provider. There are several ways the application could continue to evolve. More of the knowledge base could be packaged or cached locally, reducing the dependency on network retrieval. I could compare multiple embedded models to determine which provided the best balance of accuracy, size, memory usage, and speed. The citation system could be improved with more direct page-level source links. The test harness could use a larger evaluation model to assist with automated scoring while still preserving human review for domain accuracy. The knowledge base could also be divided into separate collections for forms, weapons, tournament rules, judging requirements, and other categories. That could improve retrieval by limiting the search to the most relevant document collection. Finally, I could build an administrative workflow that makes it easier to import updated PDFs, clean the extracted text, generate new embeddings, and re-index the knowledge base. That would make the system easier to maintain as manuals and tournament rules change. So, what began as a simple Flutter AI application became a much broader exploration of practical AI architecture. The initial prototype proved that the concept could work. Cloud AI made the first version easy to build, but unpredictable operating costs made that architecture difficult to sustain. Moving Gemma onto the device reduced the recurring inference cost, but required a stronger retrieval system and more careful engineering. Processing trusted PDFs, generating embeddings, and using Supabase vector search made it possible to provide the local model with focused source material. And building a test harness made it possible to evaluate whether the system was actually improving. The most important lesson is that building a useful AI application is not just about selecting a model. It's about designing the complete system around that model. The documents, retrieval strategy, prompts, architecture, testing process, device constraints, and domain expertise are all part of the final product. AI can generate an answer, but building an application that produces answers people can trust requires much more than AI alone.